In this videotape, we're going to talk about a number of topics, principally an overview of object-oriented programming, which is going to include inheritance, abstract classes, virtual methods, and polymorphism, and then a comparison of object-oriented programming to a concept of types and subtypes, which you have not seen before. It's not quite related to this idea of ints and strings, but is a little bit more abstract. The notes for this video lecture can be found both with briefly toward the end of Java's inheritance system, but primarily you're going to have to look into Scott chapter 9 for these notes. And also some of these topics I'll be talking about aren't really discussed well either in Scott or my online notes. So first, a very quick history of object-oriented programs. The very first object-oriented program was Simula, and it was developed in the 1960s, and it was not, strictly speaking, an object-oriented language. It introduced the concept of objects for the purpose of doing simulations, the idea being that when you simulate a system, it has a set of objects like, say, planetary bodies that are easier for a programmer to think of if they can think of them as objects. Then Alan Kay saw Simula, liked it, and developed a language called Smalltalk in the 1970s. It was actually meant to be used with the first desktop PCs. And Smalltalk really never gained a lot of traction. But in the 80s, Bjorn Strustrup added a layer to C, which he called C++, and that introduced object-oriented programming into the more conventional world of languages. Smalltalk was a very idiosyncratic language. It did have inheritance in it, which is a part of object-oriented programming, as we'll get to, but it was an offbeat language where C++ quickly became mainstream. And then, of course, Java was introduced in the 1990s. It remains the principal, or C++ and Java, probably along with C# being the principal languages that are used these days for doing object-oriented programming. Of course, there are others. The scripting languages also use object-oriented programming, but I would say these are the three major ones for doing object-oriented programming. So what is object-oriented programming? You've heard it and you probably have some ideas spring to mind, but in the programming languages community, there actually is a fairly formal definition of what characteristics a language must support before it's considered truly object-oriented. And there's three characteristics it must support. The first is it must have a concept of objects, like Simula did. The second is it must have the concept of classes, the ability to create a blueprint of a class and then stamp out instances of it. There are languages, existing languages like JavaScript, like I would say Python, that allow you to create objects without necessarily having classes that allow you to stamp them out. So they're in essence one-time only objects, whereas classes give you the ability to create multiple instances of objects. And then, if you want an example of something like that, I believe Ada gives you. It's an old defense-oriented language, kind of had a rough idea of classes without really being object-oriented. And finally, you have inheritance, and that's really the big one, is that you have to have inheritance before you have what is considered an object-oriented language. And an inheritance, as we're going to see, gives you the ability to define a tree of classes with the children nodes being refinements of the parent nodes. So without further ado, let's get into inheritance. Okay, and it's basically, I'll give you a definition and then we will go into it. So basically, it is the ability to inherit a parent class's interface, and implementation. And by interface, we're talking about the set of the public set of methods associated with the parent. And it is often, you hear an interface referred to as an API, which means Application Programmer Interface. The API is what allows a class to export its functionality to the rest of the world, yet hide its implementation so that its implementation can be changed. For example, a list might decide to change its implementation from a link structure to an array, but that implementation change would not affect the rest of the world as long as the API had not changed. So inheritance, more broadly speaking, is typically represented as a tree, and it's derived actually from science taxonomies. So we'll actually start with an example from scientific taxonomies because it shows how we can build an inheritance hierarchy either bottom up or top down. And what we're going to use is dogs, specifically Labrador retrievers. So it turns out that with Labrador retrievers, which I will refer to as labs, there's three types. There are the black Labrador retrievers with black hair, the Goldens that have kind of tannish hair, and the Browns that have brownish hair. Now, labs belong to, as defined by the American Kennel Society, belong to a group of dogs known as the sporting dogs. And there's other dogs that belong to the sporting dogs. For example, there are also what are called golden retrievers. There are the spaniels. I'll just actually, for the time being, write the spaniels. So there are other types of dogs with the sporting dogs, and then of course the American Kennel Society says, okay, you have dogs at the top of this, and there's other kinds of dogs too. There's the so-called working dogs and some other ones. And then you could go up, obviously from here you might think, okay, along with dogs you might have wolves, you might have coyotes, those might be, let's say, part of the canines, and we'll stop the hierarchy here. Hopefully you get an idea that we're doing a bottom-up approach, and what we're doing at each point is grouping common characteristics together. Okay, when you think of canines, when you think of dogs, wolves, and coyotes, you kind of have this image of dog-like face with carnivores, canines for teeth, some common characteristics. So at each level in the tree, it's kind of like everything below that level, or the subtree, all the elements in that subtree share common characteristics. Okay, let's now do a computer science example, and I'll take it from the world of graphical user interfaces. And this one will be a top-down development. So let's say that we want to model a set of graphical objects. So we might put at the top of our inheritance hierarchy graphical object. And then there's kind of two fundamental types of objects. There's box-like objects, such as rectangles, bitmaps, and text, and you have line-like objects, which are things like lines and polylines. So under box-like, we might say rectangle, which I'll just abbreviate as rect. We might say text. We might say bitmaps, okay, which would really encompass things like images. So I'll just put here images. Okay, and there'd be others, but you get the idea. Under line-like things, we'll say lines or a line. We'll also say polyline. Okay, and then you might think of other things as we go along, but for the time being, we'll just keep it with this hierarchy. And again, you can see that I developed it top-down. That's the second way to do it. Each of these shares common characteristics. And when you're developing an inheritance hierarchy, I like to think of the idea, introduce the idea of what I call factoring. So you're used to factoring in arithmetic. If you say 3 times x plus, say, 5 times x, you could write that as x times 3 plus 5. You're factoring out the x, which is a common characteristic. And that's what you're doing with interface hierarchies. You're trying to factor out common characteristics and put them in the same class. And the way you factor out common characteristics is up to you, because a lot of it depends on whether you kind of go bottom up or top down. And oftentimes you will do a mix of bottom up and top down when you're developing an inheritance hierarchy. So if we're thinking about things, oftentimes we're going to start with the bottommost thing. So for example, with a rectangle, we might start with what are its properties? Well, it probably has things like a left and a top, which is its upper left-hand corner, probably a width and a height, might have a fill color, a line color, and we'll let it at that. With text, it has many of the same characteristics. It might have a left, a top, a width, a height, and it still has a line color, which is the color in which the letters appear. In this case, you're seeing it in black. It might also have a fill color, which would be the background color. Okay, here that background color is white, but you also think text has some other characteristics. It has a font and it has some text, okay, or a label. And then bitmaps have many of these same characteristics. They have a left, they have a top, they have a width and a height. Okay, they may well have a background color. I'll call it a fill color, which is the color that appears with the transparent effects. They typically do not have a line color. And then they have some kind of image. Okay, with a line, you typically expect it to have 2 endpoints. So we'll call it x1, y1, and x2, y2. And a line style, so it might be dotted or dashed. Okay, a line color. Okay, it probably does not have a fill color associated with it. A polyline is going to have probably a set of points. Okay, so that's usually an array of points. And they also probably have a line style and a line color. And we might at this point realize that probably our rectangles might also have things like a line style. So we might go over here because it might be dotted or dashed. So as we're going along, we might figure out that objects we've already filled in have characteristics. Okay, so that's not a comprehensive list, but it may be a, let's give another one. All of them may have visibility, okay, whether they're visible or not, because that's an important thing in interfaces, is the ability to turn on and off the visibility of objects. So I'll say that all of them has a visible attribute. Okay, so now we want to start trying to factor out common things. And you can see that with our box-like objects, some of the common characteristics, I'll put it in a different color. Let's use purple for this setting. And so we have left, top, width, height, okay, visible, and fill color. Okay, line color is not common because it's not in the bitmap, and you're also, let's see, not seeing line style necessarily as a common one. So these are the common attributes. For line-like objects, it looks like it's line style and line color and visible. Okay, so these properties we would probably move up to the box-like object. So we'd get rid of left, top, width, height from the rectangle because we're going to inherit that from box-like objects. Okay, and also we're going to get rid of fill color because that is something that is being inherited, and we're going to get rid of visible because that also is something that's getting inherited. So you can see we're left with line color and line style for a rectangle, font text and line color for a text object, and image for a bitmap. If we go over to lines and polylines, we're going to get rid of the last three elements. Okay, so we're going to still store the endpoints of a line and a point list for a polyline. And notice at this point you might object and say, well, a line is really could be represented as a two-point polyline, which might be true, but often for convenience we separate out a line because it's so common. Okay, now let's look at what are the common characteristics of box-like objects and line-like objects. And we see that there is visible as a common characteristic of both of them, and that would appear to be it at this point. So we would say that, okay, we're going to get rid of the visible attribute and move it up here. And I will tell you right now that there is another common one that is kept for all objects, and that is something called a bounding box. And a bounding box is simply the smallest rectangle that completely encloses an object. So for example, for a line, this would be the bounding box. That is the smallest rectangle completely enclosing a line. For a polyline, okay, here is the most closely enclosing bounding box. And as you might imagine, for a rectangle, the rectangle itself is the bounding box. Here is the bounding box for the line object. Okay, so we'll add that as an attribute or another property of a graphical object. So now we have kind of the properties, or what would become instance variables, in our classes. So we'd have a class for graphical object, a class for box-like object, a class for line-like objects, etc. And we would need to add methods as well. So probably we would have get and set methods. So for example, for graphical object, we'd probably have get visible and set visible. So we have our getter and setter functions, or methods. And we have some other kinds of methods. So you can imagine that we probably want to be able to draw graphical objects. So we're going to define a draw method that's going to allow us to draw a graphical object. And another thing we often want to know is whether a mouse point lies within an object. So we'll define a contains point method, which is going to return true or false based on whether a point falls within an object. And now we again need to start going down our list. So we'd have probably get bounding box and set bounding box perhaps for a graphical object. Actually, the bounding box is typically computed, so we would probably only have get bounding box. We probably would not have a set bounding box because it's usually computed from the physical layout of an object. But going down, you can see the box-like objects. We'd need getter and setter functions probably for our attributes. So set left. And the same thing for things like text. We'd have to have, say, a set font and a get font. So you can see each of them has getting their own set of methods. Okay, so now moving on, we have to then, so we have our inheritance hierarchy, and as I've said, an inheritance hierarchy is meant to represent a common set of behaviors that all objects in the inheritance hierarchy are going to support. So, and they often tend to have similar kinds of implementation. Okay, so how does this relate to stuff you've already perhaps heard of or not heard of? Well, we need to introduce some terminology so we're all on the same page. So you already know about classes. Hopefully you've heard about superclasses and subclasses. So the superclass is the so-called parent class, and the subclass is the so-called child class. And a subclass is a refinement of the superclass. So it typically may add new methods, or it may add additional properties. Like in the case of the text object, it was adding properties for font and text, and it may override or change the implementation of methods. Okay, so these would be existing methods inherited from the superclass, but they may change the implementation. So when we say override, we mean change implementation. And you'll sometimes hear a superclass referred to as a base class. And you'll hear the subclass referred to as a derived class. So get also familiar with those terms of base and derived class. Also, this is hugely important, so important that I'm going to put it in a separate thing, which is that the subclass must inherit its superclass's interface in its entirety. And this is going to give a lot of you trouble at the very beginning, because a lot of times we naturally think that we can extend something and make it be a subclass. So we think of a rectangle, and you probably think, oh, a square is a refinement of a rectangle, because a square is just a rectangle with the same width and height. The problem is a square almost never supports the full interface of a rectangle. A rectangle has methods for set width and set height, whereas a square is going to pretty much want to just have a set size method. It's not going to want to have set width and set height. And this is a common issue with especially people beginning to do inheritance hierarchies, saying, well, I could just inherit set width and set height. No, you can't. Okay? The square interface does not want to support set width and set height. We will show you different mechanism called composition in a different videotape that shows you how you can inherit implementation, which is what you want to do here, when you do not want to inherit interface. So composition, we'll find out, is a way to inherit implementation without inheriting the interface. So when you inherit both the interface and the implementation. But inheritance is primarily about interface inheritance, because you're actually allowed to change the implementation by overriding methods. So it's primarily about inheriting interface. Okay, so we said that we would talk about virtual versus non-virtual methods. And the difference between the two, let's just write them here. A virtual method is one whose behavior may be overridden. Or implementation, I should say implementation, may be overridden. By contrast, as you may imagine, a non-virtual method, its implementation may not be changed, or may not be overridden. So if you think back to our graphical objects for a moment, you may remember that a graphical object had set visible and get visible. And we would make these be non-virtual methods. The reason we would make them be non-virtual is we don't want the subclasses overriding them. Okay, so a non-virtual method, its implementation has to be accepted. By contrast, we would probably make the draw method and the contains point method be virtual. Okay, because every subclass is probably going to have a different implementation for draw. A text object is going to draw itself differently than a rectangle, which will draw itself differently than a line. So we would certainly make draw be a virtual method. Same thing for contains point. A rectangle is probably going to have a different mechanism for determining whether it contains a mouse point than a line object. Okay, just think about it for a moment. If you have a rectangle, you're going to be asking whether it's contained within the bounding box of a rectangle. If it's a line, you're probably asking about the distance of the point from a line. Okay, so two different methods. So virtual methods, it turns out, cannot be, the compiler cannot determine until runtime which method is, or implementation of the method is going to be used, because it all depends on which subclass is being used. Whereas with non-virtual methods, the compiler knows at compile time which version of the method is going to be used, so it can optimize it more. We also make a distinction between virtual methods and pure virtual methods. Okay, virtual methods are ones whose behavior can be overridden but may provide a default implementation. As an example, we might provide a default implementation for contains point that checks to see whether the mouse point lies within the bounding box. And for many objects like polylines or rectangles or text objects or images, we're willing to accept this implementation. Whereas for a line, we'd probably override it. Whereas pure virtual means there is no implementation provided whatsoever. It is really an abstract method right from the get-go. So draw would be an example of a pure virtual method because there is no implementation provided for it. So pure virtual means no implementation provided. Okay. Whereas a virtual method, the implementation is provided, but it may be overridden. So that brings us then to the notion of abstract versus non-abstract classes, or what are often called concrete classes. So, abstract classes are classes that have one or more pure virtual methods, have one or more pure virtual methods. So at least one of their methods does not have an implementation defined for it. And that means you cannot create an instance of an abstract class, because if you tried to call the pure virtual method, there would be no implementation for it, hence the word abstract. Concrete classes provide an implementation for all methods, and hence you can create instances of them at runtime. Okay. Next, we come to the idea of polymorphism. Okay. And polymorphism is, you may or may not have heard about it, but roughly speaking, you think of polymorphism as a set of functions. So I'll say a set of functions that accomplish the functions with the same name that accomplish a similar task. Okay, so for example, the draw method is polymorphic because it's a set of functions with the same name that accomplish a similar task, but each of them may have a different implementation. So draw is polymorphic. But here's a different type of polymorphism. When you do a sort, okay, that's the same algorithm, but it may operate over different types. So one time it may be sorting lists, or I'm sorry, sorting integers, another time strings, and another time maybe employee records. So we actually have two different types of polymorphism that we are dealing with. One is where we have a set of functions accomplishing the same task, but perhaps with different implementations. The second, where they accomplish they have the same implementation, but operate over different types. Okay, so let's talk about those two types of polymorphism. Okay, there's two types. One is called subtype polymorphism, and one is called parametric polymorphism. So subtype polymorphism is the kind where you may have different implementations accomplishing the same task. Whereas parametric polymorphism means that same implementation over different types. Subtype polymorphism is inheritance hierarchy. Okay, so subtype polymorphism refers to inheritance hierarchies. So you have a subclass perhaps changing the implementation of its superclass. Parametric polymorphism, by contrast, typically refers to what you think of as generics or templates, where, think about it for a moment, you are providing the types as parameters. So in Java, you might say a map is indexed on an integer, and stores employees. Okay, so you just parameterized it with types. You provided a key type and a value type. That's why it's called parametric polymorphism, because you're providing the types as parameters. And there's actually two different types of parametric polymorphism. You have what is called explicit, which is what is supported by Java and C++, and you have implicit, which is supported by many functional languages. So explicit means you explicitly provide the type parameters. Implicit means that you do not, and that the language itself infers the types of the objects at runtime and performs the right comparison or the right addition at runtime based on the type of the object. So explicit polymorphism is typically associated with statically typed languages, which the objects have to have a type at compile time. Implicit is often associated with dynamically typed languages, where the type of the variable may not be determined until runtime. Okay. And finally, we come to the idea of types and subtypes, which I introduced at the beginning of this talk. And we have that there's a correspondence between types and classes. So the first thing I need to do is simply provide a definition of types and subtypes. And for that, I'm actually going to go to my notes for the Java inheritance system and go to the bottom. So a type is a set of values plus a set of operations that manipulate those values. Okay? And an abstract type is a type that specifies what its operations should do, but which provides no implementations of its operations. You've already seen such abstract types in Java through interfaces. So the collections class has like list, queue, map. Those are abstract types. There is not they define a set of methods but no implementation for their operations. Subtypes then, or let's then say concrete types. Concrete types provide implementation. So for example, hash map and tree map are concrete types that provide implementations of the abstract type map. Now you can also have a subtype, and a subtype is a type that permits the same values as its supertype, but it also provides one or more operations. So you kind of saw that with graphical objects and their subtypes. So you have graphical object, so you have a graphical object, and then you have a box-like object, and then you, let's say, have a rectangle. So a box-like object is a subtype of a graphical object, and a rectangle is a subtype of a box-like object. And an important thing is that you can use a subtype wherever its supertype is used, because the subtype has to support the same interface. And that's why I was so insistent earlier that when you inherit your parents, or you inherit from your parent, you must inherit its complete API, because you can be used in lieu of your parent. So when I have a list, I can actually say list, say x equals a new array list, because an array list supports all of the methods that a list supports. So I can use a subtype wherever I have a type. Now, the question often comes up, if I now am using X, could I use some method that an array list defines that a list doesn't? And the answer is no. If array list has a method, say, that allows me to do get some index, and let's say a list doesn't, then this would give me an error because the only methods supported by the only methods I can access right now are those supported by a list. So when I assign a subtype to a supertype, I can only now access the supertypes methods. And there is a relationship between types, classes, and inheritance. Okay, and for that I am going to go back here. So a type is a class. Okay, so a class, here we have type, over here we have a class. What is a subtype? Well, an implementation of a subtype is a subclass. Okay, what is an abstract class? Well, an abstract class is simply an abstract type. Okay, so we have already seen in Java briefly interfaces, which we'll talk about later, but in Java, the interfaces that we've seen so far, they are abstract types. And rather than having typically an abstract class, we would use an interface. So I know we've covered a lot of material in this videotape, but the important things that you want to get out of it, going back to the very beginning, is the idea that we have, with object-oriented programming, we have inheritance, we have a notion of abstract classes that are simply abstract types, we have virtual methods which give us the ability to change the implementation, and non-virtual methods which may require us to keep the same implementation. Polymorphism, which is two different types. We talked about parametric, which is like the generics because it's the same implementation but different types, versus subtype, which is the type that you see in inheritance hierarchies, meaning same task but different implementations. And then we finally talked about types and subtypes and their correspondence to classes. We will talk about actual inheritance in C++ and in Java in separate videotapes.